Hello, in this lecture, I'm going to talk about the cluster analysis in auditing. First, let's take a look at what is cluster analysis, or we could also call it clustering. Clustering is a useful technique for grouping data points such that points within a single group or cluster are similar, while points in different groups are different. So, like here in the slides, these points that look similar are grouped together to form three clusters. In general, the greater similarity within a group and the greater difference between groups mean the better clustering result. So we need to maximize the intercluster distance and minimize the intracluster distance. So basically, clustering can be used for data exploration and also to understand the structure of the data. Without the prior knowledge about data, cluster analysis can be used to search for common characteristics of subgroups in the data. And generally, the purpose of performing cluster analysis is to ask the question whether a given group can be partitioned into subgroups which have different characteristics, where the subgroups or clusters can be named or defined using the common characteristics of the group members, such as group mean for the numeric values of the representative of the observations in the group, or using the most common or majority value in the subgroups. Cluster analysis has been developed throughout the years in many disciplines. For example, management science, marketing management, the biomedical science, and computer science. There is no single dominant discipline, while the purpose or the benefit of the cluster analysis depend on the type of the applications. For example, in marketing, cluster analysis may be used mainly to learn about market segments and to see a better understanding of buyer behaviors by identifying homogeneous group of buyers. In medical science, patients can be clustered based on symptoms to understand the causes and to help finding alternative therapies. While in psychology, cluster analysis is used to understand the relationship between health risk and college students' health behaviors. Okay, then let's take a look at some definitions in clustering. The first important definition in clustering is called the well-separated cluster definition. It's saying that a cluster is a set of points such that any point in the cluster is closer or more similar to every other point in the cluster than to any point not in the cluster. Sometimes a threshold is used to specify that all the points in the cluster must be sufficiently close or similar to one another. While this idealist definition of a cluster is satisfied only when the data contains natural clusters that are quite far from each other. This figure gives an example of well-separated clusters that contain three clusters. The distance between any 2 points in different groups is larger than the distance between any 2 points within a group. Well-separated clusters do not need to be circle, but can have any shape. However, in many sets of data, a point on the edge of a cluster may be closer to some object in another cluster than to object in its own cluster. For example, if this circle is very large and also this one, so the border points may be closer to each other. In this circumstance, many other cluster criteria have been developed. For example, center-based cluster is one of these cluster criteria. It said that a cluster is a set of objects such that an object in a cluster is closer or more similar to the center of the cluster than to the center of any other cluster. The center of a cluster is often a centroid, which is the average of all the points in the cluster, or it can also be a monoid, the most representative point of a cluster. Okay, another alternative cluster criterion is called contiguous cluster definition, or we could also call it nearest neighbor or transitive clustering. According to this definition, a cluster is a set of points such that a point in the cluster is closer or more similar to one or more other points in the cluster than to any point not in the cluster. So if the data is represented as a graph, where the nodes are objects and the links represent connections among objects, then the cluster can be defined as a connected component, like a group of objects that are connected to one another, but that have no connection to objects outside the group. We can see in this figure that even these two groups of points are not located together, but there are some connections between these two groups of points, so we still consider the points in one cluster. Okay, then another definition of cluster is called density-based definition. According to this definition, a cluster is a dense region of points which is separated by low density regions from other regions of high density. This definition is more often used when the clusters are irregular or intertwined, and when noise and outliers are present. So we can see that this figure is very similar to the figure in the last slides here, but we just add some noise. So according to density-based definition, like here, there's two groups of points are separated into two clusters because the density of the noise is lower than the density in these two group of points. So we can see that the density-based definition is very good to deal with noise and outliers compared with the contiguity-based definition. In the contiguity-based definition, the noise here between these two clusters may form a bridge to connect these two clusters together. Then I'm going to introduce several different types of clustering. The first is the exclusive and the overlapping clustering. We can see that in the exclusive clustering, each object is assigned to a single cluster. Like here, there are three clusters, and the one object belongs to one cluster or not. If an object can simultaneously be assigned to more than one group, then we call it overlapping or non-exclusive clustering. You can see that here there are still three clusters, but there are some points like the point K, it belongs to this cluster, or also it belongs to this cluster. The overlapping clustering is usually used when an object can equally be assigned to any of the groups. Then the second type of clustering is the hierarchical and the partitional clustering. Like here we can see that in this figure, it shows a hierarchical clustering. We see that there are 1, 2, 3, 4, 5 clusters, but some cluster belongs to the other cluster, so we call it hierarchical clustering. While in the partitional clustering, we see the figure here that the clusters are separated partitionally. There are no clusters belong to the other cluster. Then also there are other types of clustering like the complete and partial clustering. For a complete clustering, it assigns every object to a cluster, while for a partial clustering, it doesn't assign every object. Usually the objects which are not assigned to any cluster can possibly represent noises or outliers. Like when we discussed the density-based cluster, the outliers between those two group of points are not assigned to any other clusters, so it's a partial clustering. While also we can distinguish clustering to the hard clustering and soft clustering. In the hard clustering, each object belongs to a cluster or not. In the soft, or we can call it fuzzy clustering, each object belongs to each cluster to a certain degree. It's like a likelihood of belonging to the cluster. So usually in the fuzzy clustering, it assigns membership a weight between 0 to 1 for every object to every cluster. So the 0 means that the object is absolutely not belonging to this cluster, while 1 means that the object is absolutely belonging to one cluster. While any points between 0 and 1 means that this object maybe has like 0.3 possibility to belong to this cluster and have 0.5 possibility to belong to the other cluster, like this. Okay, then let's take a look at the steps in the cluster analysis. The cluster analysis is generally started with observation measurements. Observations are measured on k variables usually. The observations' similarity distance between each pair of observations are measured. After that, then some algorithm will be employed to group the observations into subgroups based on those observations' similarities. Then clusters are formed. The goal is to create the clusters which have small within cluster variation but large between cluster variation. And finally, clusters are compiled. The difference between clusters can be seen from the representative values such as mean values of the input variables from each cluster. The two major steps in cluster analysis are selecting measures of similarities or dissimilarities and select the procedures for cluster formations. There are several options or techniques available for these steps, making cluster analysis as much as art as a science. Okay, then I'm going to go through these steps in detail. The first step in the cluster analysis is to prepare the data, to make the data usable for the following steps. Okay, And the first stage in the data preprocessing is called data cleaning. Data cleaning is a process of detecting and correcting or removing the corrupt or the inaccurate records from a database to improve the data quality. And usually, the common data quality issues in the raw data, in all kinds of raw data, include the inconsistent representations of the same concept, the missing values, the outliers and the duplicates that due to entry errors. There are some errors that you can identify very obviously due to the errors are not the fraud. Okay, after the data cleaning process, usually we need to do some descriptive statistics and visualizations to understand data, like we discussed in some previous lectures. The descriptive statistics we usually used include the sum, the mean, the max, and the minimum values of a certain variable, and then the standard deviation, or we count the total numbers of some variable of the record, and then the frequency distribution of the variables. Also, we use some histogram or graphing, some kind of this or different visualization techniques we have talked before to visualize the data, to understand data better. And sometimes we need to do some data transformation to make the data more suitable for our goal. These two figures demonstrate a data transformation example. You can see that this is medical claim data or insurance claim data. It's based on each transaction. So each record represents one transaction, one the insurance claim. And you can see that the attribute includes the patient ID, the patient sex, some like patient information, or also the physician's information, like the physician ID, the location, specialty, or some like claim information like the charge or the time of the claim. For example, if we want to focus on the patient, not on each transaction, so we may want to reorganize the data, like to aggregate some fields, and so that we could use this reorganized data in the model we may want to use in the following steps in the cluster analysis. So this table below the raw data shows transformation of the raw data, like we reorganize the data according to the patient. So each record represents one patient. Then we still include the patient information, like the stacks or patient ID. And then we aggregate the patient's usage of the insurance for a certain time period. So we have the total number of services the patient have used during this period, and the total number of physicians the patient has seen, or the average charge per services of this patient during this time period. So based on this reorganized table or the data, we could cluster the patient according to their usage of the insurance system. Okay. Another step in the data preparation stage is called feature selection. Feature selection aims to select features or select attributes out of the original fields to maximize the discrimination power of the statistical methods in separating abnormal and normal cases. Well, there are many technologies that we could use to choose the features. Like we could ask the domain expert for they could give us some suggestion, or we could use some other statistical method to do the feature selection. Okay, then after we prepared the data that to make the data usable for the cluster model, then the next thing is we need to define the similarity between the objects. Because the goal of the clustering is to group together the similar data. So the first thing we need to consider is what is similar? What makes the data similar? So there is not a single answer for this question. It depends on what we want to find, or it's very related to the data. So this is one of the reasons why we call clustering an art more than a science. So the similarity measure is often more important than the clustering algorithm we used. So it's very critical for this step that we choose the similarity measure. And sometimes instead of we talking about the similarity measures, we equivalently refer to the dissimilarity measures. Is that how we could define the dissimilarity of the objects? So as I said that the choose of the similarity or dissimilarity measure is very depend on the data type. So usually let's go back a little bit review of what kind of data we usually refer to. So in clustering analysis, the data type we may deal with include the interval scaled variables, which is the continuous variables or quantitative variables we have discussed before. Also, we have the binary variables, which is the dummy variables with 0, 1 variables. And we also have the nominal, ordinal, and ratio variables that we also discussed in the descriptive statistics. And we may have the mixed type of these variables. Okay, so first let's take a look at this similarity or similarity between the interval scaled variables or the quantitative or continuous variables. So usually we use distance to measure the similarity or dissimilarity between two quantitative variables. The popular distance function we use in the clustering is the Minkowski distance. This formula demonstrates the calculation of Minkowski distance between two p-dimensional data objects I and j. Like we first calculate the difference between each attribute in these two data set, like xi1, then we minus xj1, and then we times the q, which is a positive integer, and then we calculate the root of the total sum, then get the distance. Okay. Like if q equals to 1, then the distance is we could Manhattan distance. We just need to use the difference between the each attributes of these two data objects. Well, if the q equals 2, then it is the Euclidean distance. This distance is one we usually use in the two-dimensional condition. It's just like we calculate the one side of the triangle. Also, we could also use the weighted distance, the parametric product moment correlation, or other dissimilarity measures. But the similarity measures the distance between the interval scaled variables are the most usually used one. Then for the binary variables, we may use different distance calculation method. For example, we still for these two data objects I and j. But if each attribute for these two objects are the binary variables, like the value of each attribute is either 1 or 0, so we could get this contingency table for these two binary data in order to calculate their distance or dissimilarity. This table shows that if one attribute in object j equals to 1, and it also equals to 1 in object I, then it will fall into this situation. And then we calculate how many attributes are in this situation. For example, there are A attributes in this situation. Then there are B attributes which have 0 in object J and have 1 in object I. And there are C attributes which have 0 in object I and have 1 in object J. And there are D variables that have both 0 in object I and in object J. Okay, then if this binary data is symmetric binary variable, which means that there are no value 1 and 0 have the equal significance, have the equal importance. So we call this kind of binary variable is symmetric binary variable. In this case, we use this function to calculate the distance between these two variables. First, we add the number of variables that have different values in these two objects, so which is b plus c, and then we divide by the sum of the variables in both of these two objects equals to a plus b plus c plus d. Okay. While if this variable this binary variable are asymmetric binary variable, which means that the value 1 is more important than the value 0. In this case, we may not care how many variables are both equals to 0. So we use a different distance or dissimilarity measures for these two asymmetric binary variables. And usually many of these binary variables are asymmetric. So in this case, we still calculate them. First, calculate the number of the attributes that have different values in both of in these two objects, like it's also equals to b plus c, and then we just calculate b, add c, and then add a. So in this case, we don't care the d because it have 0 in both of the objects I and j, and the value 0 is not that important as the value 1. Okay. So this is the math. This is the formula to calculate the dissimilarity between two binary variables, while the formula to calculate the similarity between the asymmetric binary variables is the most usually used one is called Jaccard coefficient. Its formula is like this. So instead of calculating the distance or the dissimilarity, here we calculate the similarity. So we just use the attribute, the number of attributes that have the same value in both of these two data objects, which equals to 1. Because we don't care the 0 value, so we don't add D. So we just use A here, then we divide A plus B plus C to get the similarity of these two asymmetric binary variables. Then I'm going to show you an example for this calculation. For example, we have this data set, which have 6 variables, 1, 2, 3, 4, 5, 7 variables. Like we can see that the first variable, gender, is a symmetric variable because the male or female have equal importance. While the other variables like fever, cough, the test 1, 2, 3, 4, they are asymmetric binary variable because the fever equals to yes are more important than the fever equals to no. Okay? So for this 6 asymmetric variable, then let's calculate the distance, this similarity between these 3 data objects or 3 persons. We are based on these 6 asymmetric binary variables. For example, we let the value y and p positive equals to 1 because they are more important, and then we let the value n or negative equals to 0. In order to calculate the distance or dissimilarity between Jack and Mary, we first need to calculate the different value of these two data objects. Like we can see that here there are 1, the result of test 3 is different from Jack and Mary. So we have 1 difference here, it's 1. And then we calculate the number of ones. We have fever, both of them are 1. We have test 1, both of them are 1. So we have 2 ones. And then let's test off. Then we add to the add the 2 ones to the 1 difference to get the 3. So the distance between Jack and Mary is 1 divided by 3 equals to 0.33. Then let's take a look at Jack and Jim. First, we also to calculate the difference, like cough here, and the result of test 1 is 2 difference value between Jack and Jim. So there are 2 difference between Jack and Jim. Then we need to add the ones here, like they both of them have fever, and so this is only 1 variable that have 1 in both of these 2 data objects. Then we just need to add 1 to get a 3. So for Jack and Jim, we just need to use 2 divided by 3 to get their distances 0.67. And then we look at Jim and Mary. to see their difference too. Like there were three. Actually, there are three attributes that are different for Mary and Jim, while they have only one that have one in both of these two data objects. So we use the 3 plus 1 to get 4. Then we just use 3 divided by 4 to get the distance between Jim and Mary, which equals to 0.75. Okay, so I think according to this example, you will understand how to calculate this similarity between the binary variables. Then let's take a look at the nominal variables. First, let's just take a brief review of what is nominal variables. Nominal variables is a generalization of the binary variables in that it can take more than 2 states. Like it's not 0 and 1, it could be 0, 1, 2, it could be red, yellow, blue, green. So usually there are 2 methods to calculate the distance between this similarity between the nominal variables. The first one is we call the simple matching. We just need to calculate the number of matches between the 2 data objects, and then we use the total number of variables minus the number of matches to get the number of mismatches. The unmatched number, then we use this unmatched number to divide it by the total number of variables to get the distance. If we need to calculate the similarity, then we just need to use the number of matches to divide it by the total number of variables. Okay, then the second method that could be used to calculate this similarity between nominal variables is use of large number of binary variables. Like we change each, we create a binary variable for each value of this nominal variables. Like to form a vector for each nominal variables. Like red, we could choose 1 or 0, yellow is 1 or 0, blue is 1 or 0, green is 1 or 0. Then we just calculate the distance using the Jacquard or any other distance that we can use for the binary variables. Okay, then I think you will still remember that another variable is the ordinal variables that have rank. That order is making sense in the ordinal variables. So we could try to treat the ordinal variables like interval scales, or to transform the ordinal variables into interval scales. First, we could replace the value in the ordinal variables using their rank to create interval scaled variable, or to create a continuous variable. And then we could map the range of each variable onto the 0 to 1 range by replacing the ith object in the fth variable using this formula. Then finally we could calculate the dissimilarity of the ordinal variables using method for interval scaled variables. Okay, Another variable that we may not discuss before is called the ratio scaled variable. It's just exponential scale the variable. It seems very difficult to calculate the distance between the exponential scale variable. So we also need to convert or transform this kind of variables into the other easy calculated type of variables. We may want to treat them like interval scaled variables, but maybe it is not a good choice because the scale can be distorted if we directly change the exponential scaled variable to interval scaled variables. But we could apply logarithmic transformation to transfer the ratio scale data to ordinal data. And then we just use the way that we treat the ordinal data to transfer them to interval scale data, again, to calculate the dissimilarity between the exponential scale data. Okay, after choosing the similarity measure, then we need to choose a certain type of clustering method to do the clustering. While there are several different kinds of existing clustering methods, including the centroid-based, density-based, hierarchical, graph-based, and probabilistic clustering method. Then I'm going to show you each type of this clustering method one by one. First, let's take a look at the centroid-based method. This method is related to the center-based cluster definition. And one of the most popular clustering method belongs to this centroid-based method is called k-means clustering method. The k-means clustering method is simple. I first choose the k initial centroid, and k is a user-specified parameter, namely the number of clusters that designed. Okay, for example, in this example, the k equals to 2. So the users want to find 2 clusters from these points. And then each point is assigned to the closest centroid. And each collection of points assigned to a centroid is a cluster. Like at the beginning, for this, because these 2 points are selected as the centroid, then the cluster in the second stage is like this. So the 2 clusters like this. And after this, the centroid of each cluster is then updated based on the points assigned to the cluster. Then it means that the algorithm will then recalculate the centroid based on this point. Then you can see that the centroid is moved from here. Okay, these 2 points, red points. And after this, the algorithm will repeat the assignment. So using this 2 point centroid, then it will reassign the points. So then the cluster will be like this. It is different from the first cluster. And then the program will update the centroid again and repeat this circle again and again until no point changes in the cluster, or until the centroid remains the same. So finally, you will find a two clusters that were different from the two clusters that formed in the first stage. Okay, and if the centroid doesn't change, it keeps the same. It means that it is in a stable stage. So and it's in the optimized stage. That these two clusters are the best clusters. Okay, so this is the centroid-based method. And then another method is the density-based method. Also, it's related to the density-based cluster definition. In the density-based method, the clusters not clustered according to the distance between the cluster centroid. It's clustered according to the density of the points. And the most popular algorithms for the density-based method is called dbScan. According to this method, the data point falls into three classes. The core points, here like the points here, these are points that are at the interval of a center of a cluster. A point is an integral point if there are enough points in its neighborhood, like if the number of points within a given neighborhood around the point exceeds a certain threshold. This threshold is a parameter that defined by the users. So if two core points belong to each other's neighborhood, then the core points belong to the same cluster. And then the other type of points in the density-based method is called border points, like some points here. A border point is a point that is not a core point, like there are not enough points in its neighborhood, but it falls within the neighborhood of a core point. And then the third type of points in this method is called noise point. A noise point is any point that is not a core point or a border point. Therefore, in the density-based method like dbScan, a cluster is a set of all core points whose neighborhoods transitively connect them together, along with some border point. One outlier will be discarded. Then the other type of clustering is hierarchical clustering. It groups data objects into a tree of clusters. In hierarchical clustering, the goal is to produce a hierarchical series of nested clusters, ranging from clusters of individual points at the bottom to an all-inclusive cluster at the top, like here. Here, at the bottom of the tree, every point forms a cluster, while in the top of the tree, all the points are in one cluster. One of the attractions of hierarchical techniques is that they correspond to taxonomies that are very common in the biological science, like the kingdom or genus or species. Also, some cluster analysis work occurs under the name of mathematical taxonomy. And another attractive feature is that hierarchical techniques do not assume any particular number of clusters. Instead, any desired number of clusters can be obtained by cutting this tree at a proper level. Finally, hierarchical techniques are thought to produce better quality clusters. There are two basic approaches to generating a hierarchical clustering. first one is agglomerative. It starts with the points at individual cluster, and at each step, it merged the closest pair of clusters. Like this one is called agglomerative cluster. It starts from the bottom of the tree and then goes to the top. This requires defining the notion of cluster proximity. While another approach to generate hierarchical cluster is called divisive. This one, it starts with one all-inclusive cluster, like at the top of the tree, and at each step, it split the cluster until only single clusters of individual points remain. In this case, we need to decide which cluster to split at each step. In a simple divisive algorithm, it first computes a minimum spanning tree for the proximity graph, and then it creates a new cluster by breaking the link corresponding to the largest distance. Like this one, these two clusters have largest distance, or the smallest similarity. And then it repeats this step to break the link until each cluster only have one object. And the basic agglomerative hierarchical clustering algorithm is first it calculates the approximate graph if necessary. Sometimes the approximate graph is all that is available. That is every available objects, and then it merges the closest or the most similar two clusters, like these two, they may, and these two, they may more similar than the others. Then it updates the approximate matrix to reflect the proximity between the new clusters and the original clusters, and then it repeats the merging until only one single cluster remains that includes all the objects. Then another clustering method is called graph-based clustering method. Although like in the hierarchical clustering algorithms that we discussed in the last slides, it can be viewed as operating on a proximity graph. However, they are more commonly viewed in terms of merging or splitting clusters, and often there is no mention of graph-related concepts. But there are some clustering techniques that explicitly cast in terms of a graph or a hypergraph. So in a graph-based clustering method, it first will start with a proximity matrix and then consider each point as a node in the graph, and each edge between two nodes has a weight, which is the proximity or the similarity between the 2 points. Then we just need to cluster the points that have the also most similarity together to form the clusters. So another clustering method is the probabilistic clustering method, which typically shows as a model in an attempt to optimize the fit between the data and the model using a probabilistic approach. So each cluster can be represented by a parameter distribution like a Gaussian or Poisson, and the entire dataset is therefore modeled by a mixture of these distributions. So distribution-based clustering provides faster and natural cluster of very large dataset, and it could automatically determine the number of clusters to be generated, which is good as a density-based clustering method. Okay, So after we choose this similarity or similarity measure and the clustering method, there are some other considerations during the clustering process. The first one is choosing the number of clusters. This is one of the most important decisions in performing cluster analysis. Clustering always finds subgroups of clusters, however, determining which groups are meaningful is the significant task. Several techniques can be used for estimating the number of clusters, some of which are very straightforward, while others are quite subjective. Like the techniques for selecting the number of clusters include that the data can be plotted into 2 or 3 dimensional space, and then we could examine the data. Then also we could validate the groups manually by checking the meaningfulness of the groups in some simple data set. And then we could also looking at the difference between levels in the trees. A good sleep can be identified in the hierarchical clustering. Another thing we need to consider is the number of data objects. Clustering can be affected by the number of data objects. The cluster analysis requires powerful computing because computations can be extensive, especially as the number of objects increases. To include or exclude a certain observation can have an effect on the cluster's forms. Ideally, all observations assuming no outliers should be included in clustering procedures so that the cluster results are a true representation of the dataset. And another consideration is the number of attributes. The algorithms that work well in low dimensions may not work well in high dimensions. In other words, algorithms that work well when there are fewer attributes, such as 1 to 20 attributes, may not give a great result when there are a large number of attributes, such as 100 different attributes. So the relationship between attributes can also create difficulties in cluster analysis. Moreover, using a small number of attributes may be easier for clustering procedures. However, the results may not be useful. On the other hand, using many attributes at the same time may complicate the procedure. Finally, noise and outlier also need to be considered. The outliers or noises can affect the performance of the cluster algorithm. In some techniques, such as the hierarchical clustering, the outliers can result in joining clusters which should not be joined. Therefore, data might have to be pre-processed to remove outliers before performing cluster analysis. While some algorithms, like density-based algorithms, can detect or identify objects as noise and move them from clustering procedures. That kind of um, algorithms may be better to deal with the data that including the outliers. Okay, finally, after we finish clustering step, we need to evaluate the clustering result. Because some of the methods that gave statistically meaningful results will not necessarily give managerially meaningful results. And because clustering is an unsupervised learning algorithm, there is no label for data. Its goal is trying to determine to which group each data in unlabeled data set belongs. There is no absolute best criterion to decide which clustering algorithms give the best clusters. It must depend on users' need. The best clustering techniques are those that can provide the results which are useful for the user's purposes. Cluster evaluation and interpretation are quite subjective, though the clustering results can also be interpreted in different ways. The meaning of each cluster should be intuitive. In general, a good cluster algorithm is one that produces clusters which the intra-cluster similarity is high, while inter-cluster similarity is low. However, the measure of the similarity is also a challenge. There are several techniques and measures for similarity to choose from. And the type of similarity measures should fit the type of data, like we have discussed before. And some measurements may be good for one dataset but not for the other. A cluster algorithm can also be applied to a dataset with a natural cluster and produce poor quality clusters simply because the wrong similarity measure have been chosen. Well, when good quality clusters are defined to get a general idea of how the clusters are different, the means and the variance of each cluster should be compiled. Examining the representative values of the clusters will help in understanding the distinguishing values and the characteristics of each cluster. All clusters should have enough observations to be meaningful for the interpretation too. Having too small or too big clusters can mean that the number of clusters selected is not appropriate for the dataset. Not only a small cluster can mean that the number of clusters selected is too large, but the small cluster can be an outlier or abnormal. On the other hand, having a cluster which is too large dominating the result can mean that the number of clusters selected is too small. Okay, then let's take a look at the applications of cluster analysis in business. Basically, clustering is a widely used technique in the area of marketing research, especially the market segmentation, the market structure analysis, and the study of customer behavior. Also, in the social science, the cluster analysis is used similarly to market segmentation in the marketing. So there is much potential in the usage of the cluster analysis in the auditing or accounting to understand the nature of accounting transactions. There are very few studies have been performed. So in this lecture, I'm going to introduce two applications of audit risk, two applications of using cluster analysis in auditing. The first one is use cluster analysis in the explorative data analysis. It is basically use cluster analysis to help auditors gain understanding about the data and identify the possible risks and problems with the system. Besides the explorative data analysis, clustering as an unsupervised learning algorithm is a good candidate as a fraud and anomaly detection technique. It is difficult to identify suspicious transactions, while clusters can be used to group transactions so that different treatments and strategies can be applied to each different cluster. So first I want to demonstrate an application of the cluster analysis that used to do the exploratory data analysis in auditing. So basically, the practical data analysis can be divided into two phases, the exploratory and the confirmatory. And the exploratory data analysis is used to help users understand the data and to search for clues and evidence in the data. When auditors is planning an audit, they need to understand the client and their data in order to plan effective and efficient audit procedures. So the exploratory data analysis can be used in the audit planning stage to help the auditors. And basically, there are several methods that auditors can use to obtain information and knowledge about the client and the data, like the descriptive statistics we have discussed, and the data visualization techniques using the graphs or charts to visualize the data. But in addition to this classic statistical method, the powerful data mining methods are gaining popularity as computer systems become less expensive. These techniques use artificial intelligence for machine learning, but whether using statistical or machine learning methods, the objective of the data exploratory task is to construct classification schemes over an initial unclassified set of data. While cluster analysis, which is one type of machine learning data techniques, is used as an important exploratory tool for knowledge discovery in the other disciplines. So in this application, we will also try to use cluster analysis to do the exploratory data analysis. Generally, the audit problem for this application is that this application or this research deals with a large international bank that identified transitory account as a major area of risk. The transitory account acts as a temporary resting places for bank transactions that cannot be completed immediately after being entered into the bank's system. The transaction is kept in a transitory account until the issue is resolved. The problems involving the transitory accounts may include a non-existent destination account for money transfer, the higher transaction amount than the balance of the account, in an inactive account, etc., etc. Once the problem is resolved, the transaction is cleared, then the remaining balance should be equals to zero. The questions about what happens to the transactions posted to transitory accounts are of great concerns to the bank. Large incorrect entries could eventually create materially incorrect financial statements and substantive losses due to fraud or error. Consequently, transitory accounts are included in a continuous auditing program aimed at monitoring key accounts and filtering potential fraudulent transactions. But little information is known about the transitory account's regularity or behavior. Therefore, it is a suitable scenario for exploratory data analysis. The auditors will gain understanding about these transitory accounts and identify possible risks and problems with the system. So the related audit the management questions include: why does a transaction end up in transitory account? What was done to resolve the issue with the transaction? Was the appropriate action or change taken for the transactions proper? So the data used in this research is the sample transaction dataset covers the period from January 2008 to December 2008. It encompasses information from 16 transitory accounts that have been pre-selected by the bank as the accounts of interest. Like this table listed this transitory account. And the purpose and origin of each transitory account is different. For example, the account 302 is for operations in process, which is a form of interdepartmental transfer, and the account 61930 is for wire transfer for financial applications, and the account 70015 and 70068 are for return of interdepartmental transfer. But no matter where these transactions originated from, they are posted to the transitory account because the system cannot complete the transactions at the time they are presented. The problem can be for various reasons, including incomplete account numbers, incorrect account numbers, insufficient funds, etc., etc. And there are 16 attributes extracted for each transaction. And also this table listed these 16 attributes, where the first 3 attributes, like these 3, are identification types. They provide the branch number, like here, the branch number, the account number here, and the transaction number here. 4 of the attributes provide information related to date and monetary value when the transaction is original posted and when the transaction is last posted on the transitory account. Like here, the date of last entry, the date of entry in the table, and the amount, residual amount. Okay. While 6 of the attributes are no longer used by the bank, like this one, season of origin, that fit the table, not used anymore, like this last 6 attributes. 2 of the attributes give information on the nature of the transaction. Like this one, it indicates whether the transaction is debit or credit. And also, this one is indicate whether the transaction is automatically entered or manually entered. The attribute which appears to contain the most detailed information related to the transaction is comment field, or this field comment. This attribute is rich with information content. It can contain much of detail such as account number, branch number, dates, reasons why the transaction is posted to the transitory account, and etc. etc. This information can be automatically entered by the system, manually entered by an employee of the bank, or a combination of both. So generally, there is no prefixed format of how the comment should or could be entered. Though this attribute appears to contain valuable information, it is extremely difficult, if not impossible, to process the information for further analysis due to its free field format. Therefore, a parsing procedure is developed to make the attribute readable and understandable to the computer system. The parsing procedure aims at breaking the comment into smaller and more manageable form. So we use this parsed comment field as the input variable for our clustering procedure. And because neither the distribution of the input variables nor other parameters necessary for cluster analysis is known, we use the expectation maximization algorithm for this clustering method. The expectation maximization algorithm involves 2 steps. First, expect the cluster possibilities. And second, it maximizes the likelihood of the distributions given the data. So for this method, only the cluster probabilities, nor not the cluster themselves, that are known for each observation. Though the free-form comment field has no standardized format, it could be parsed or separated into 4 parts. Most transactions have the branch and account number as the first 2 parts of the free-form comment. The remaining 2 parts are mainly coded message, like the coded number and the written message. Because the first 2 parts of the comment are mostly the same, it is justable to select part 3 and part 4 for visualization purpose. And this figure shows the result of this cluster analysis. Transactions having similar comments are grouped into the same cluster. From this graphical visualization, it shows that there are 7 clusters, like from 0, class 0, 0, class 1, class 2, class 3, class 4, class 5, and class 6. And the dots represent individual transactions, while the same colors represent the same clusters. And this figure highlights that the most grouped transactions created large areas of a single color. There are areas for yellow, like here, green, purple, here, red, light blue, and blue here. The x-axis represents part 3 of the comment here, and y-axis represents part 4. The large area of single color demonstrates that the transactions from the same cluster has the same values in class 3 and class 4. Then we analyze a dataset that consists of transactions entered into a single transitory account by over 1,000 branches of a major foreign bank. Some branches are bigger and originate more transactions than others, while the number of transactions by branches range from 1 to over 1,500 transactions. The top 20 branches, in terms of number of transactions originated, comprise 20% of the total number of transactions in the transitory account. In order to gain a better understanding of the dataset, the clustering result by branch is examined, and the distribution of the clustered transactions of the top 20 branches is examined. And the result is shown here. We found that different branches have different dominating types of comments. Examine transactions from a particular transitory account in a particular branch. There should be only one cluster, and the transactions from clusters other than the one with the highest population may be considered an anomaly. So we can also see in this picture, in this figure, that usually there is a dominating cluster for each branch. So like this, if in a certain branch there are some very small clusters, like here, for this branch you have these 2 small clusters, or in this branch you have this several small clusters. Then these transactions may indicate the abnormal transactions, and they may be the potential fraudulent cases. So these transactions need further investigate by the auditors. Okay, so this is the application of a cluster analysis to do the exploratory data analysis in auditing. Then let's take a look at anomaly detection. Basically, the anomaly detection is used to detect the outliers. Outliers are observations that deviate significantly from other observations to the point that they generated by a different mechanism. Anomaly occurs for many reasons, for example, the different classes of data, the natural variation in the data and the data measurements, and the collection error. What anomaly basically can be classified into three categories: point anomaly, contextual anomaly, and collective anomaly. Point anomaly is a simple form of anomaly that identifies an individual data instance as anomalous in respect to the remaining of data. Contextual anomaly occurs when the data instance is anomalous in specific context. For example, a temperature of 35 degrees is considered normal in winter, but rather abnormal in summer. While collective anomaly is the case when a collection of related data instances are anomalous. And there is a possibility that many abnormal events have both temporary and spatial locality, which might form small clusters that also need to be deemed as outliers. In other words, not only single points, but also small clusters can probably be considered as outliers. This type of outlier is called a cluster-based outlier. While abnormal detection is a task of identifying observations whose characteristics are significantly different from the rest of the data. These observations are called outliers or anomalies because they have attribute values that deviate significantly from the expected or typical attribute values. Application of anomaly detection includes fraud detection, credit card fraud detection, network intrusion, etc., and etc. Regardless of the applied domain, anomaly detection generally involves three basic steps. First one is identify normality by calculating the signature of the data. The second is determining the metric to calculate an observation's degree of deviation from the signature. And the third is set some criteria or threshold to identify anomalous observations which metric measurements are higher than the threshold. A variety of methods for each step have been used in various applications in all fields. With respect to the extent to which the labels are available, anomaly detection techniques can be operated in one of three modes: the supervised anomaly detection, semi-supervised anomaly detection, and the unsupervised anomaly detection. Supervised anomaly detection assumes the availability of a training dataset which has instances labeled as normal as well as anomaly classes. The semi-supervised anomaly detection assumes that the training dataset has labeled instances for only the normal classes, while a model corresponding to the normal behavior will be built and used for identifying the anomalous instances in the test data. While unsupervised anomaly detection doesn't require a training dataset, it assumes that anomalous instances are far less than the normal instances. While cluster analysis is one kind of this unsupervised anomaly detection technique. Okay, then specific for the cluster analysis for anomaly detection, this can be grouped into three categories. The first group relies on the assumption that normal data instances belong to a cluster in the data, while anomalies do not belong to any cluster. Basically, these techniques apply a clustering algorithm to the dataset and declare any data instances that do not belong to any cluster as anomalous. While the second group relies on the assumption that normal data instances lie close to their closest cluster centroid, while anomalies are far away from their closest cluster centroid. The techniques in this group basically involve two steps. Firstly, grouping data into clusters, and secondly, calculating distances from cluster centroid to identify anomaly scores. The third group relies on the assumption that normal data instances belong to large and dense cluster, while anomaly either belong to small or sparse clusters. Both techniques define sparse clusters as anomalies. In other words, they determine anomalies based on the density and distance from other clusters. The choice of these three groups of techniques really highly depend on the data and the specific cases. And in the case that I want to demonstrate today, we focus on a wire transfer process in an insurance company. This insurance company is aiming at developing a continuous audit and fraud detection process. Therefore, the internal audit team of the company has cooperated with the research team or our team to develop automatic models of methodologies that could be used in parallel with the internal audit process. The wire transfer process is selected for model development because of a number of factors. First, the data is available for the analysis. Second, the internal audit team identifies that wire transfer is an important process which involves a large number of transactions in the system. And third, a knowledgeable and competent internal audit team is available to assist in the model building process. The wire transfer process in the company consists of three stages: initiation, approve, and payment. First, users in the line of business initiate or request the payment. The request is then needed to be approved by appropriate approvers. Depending on the type of and nature of the wires, some may require more approvers than others. After the request is approved, the payment is then made to the payee. Though wire transfer is a significant process, it doesn't seem yet to have a very good control set in place. There are cases where the crucial information is missing, such as approvers' identification. Specific controls that exist in the system are, for example, users are assigned to a specific transaction and bank account group. Therefore, they can conduct a certain type of transaction through specific bank account groups. The company doesn't seem to have available the record of previously identified fraud or anomalies. However, lacking of such a record doesn't necessarily mean that there is no fraud in the wire transfer process. Due to the lack of previous fraud history for model development process, applying an unsupervised method is appropriate. So we choose cluster analysis as the technique to detect the fraud in this case. Okay, then let's take a look at the data we use in this case. The data obtained from an insurance company consists of wire transactions for a period of time from 2008 to 2010. It includes information on each wire transfer, such as its approvers, initiators, senders, receivers, the department or group it belongs to, the amount it has transferred, the designated location it will be sent to, as well as its other description or information. There are 27 original attributes provided. Most attributes are mainly for identification purpose, like the initial ID, the approver ID, cost center ID, like the account number, etc., etc. Though they're very informative, they are not useful for classification. Therefore, based on the original attributes list and additional consultation with the internal auditors, attributes that represent characteristics of wire transfers are created. The first one is the wire type. There are four types of wire transfer: the random, repetitive, concentration, and batch. The categories are based on the number of payments and on operational effectiveness and efficiency. These wire transfers have different characteristics. Therefore, it is reasonable to assume that they may have different behaviors. And the second attribute is the type of payee, the individual who receives wire transfers. Payee are categorized by the number of payments that he or she received throughout the period. And the third attribute is type of initiator, the individual who initiates wire transfers. The type of initiator is identified by the number of wire transfer he or she initiates during the period. And the fourth one is a type of approver, means the individual who approves the wire transfer. Also, the type of approver is identified by the number of wire transfer he or she approves throughout the period. Then the fifth attribute is the transfer type. This attribute provides information on the type of wire transfer. And the sixth attribute is the cost center. Cost center is the relationship between the initiator and the approvers of the wire transfers. Cost center provides information related to the group or center that the specific employee belongs to for cost management purpose. Different cost center represents different branches or different business lines. There are three different types of cost center information in this dataset. The first one is initiator's cost center. The second one is approver's first cost center. And the third one is the second approver's cost center. Depending on transaction type, there should be different relationship between initiator's cost center and approver's cost center. This attribute is created to represent the relationship between initiators and approvers. It shows how close they are, like if they are from the same cost center. And the next attribute is the indication of the auto initiator. This attribute indicates whether the initiator is an automatic system or a person. It is defined by using the characteristic of the initiator identification. For a regular person, the identification would be numbers. An identification of an automatic system can be alphanumeric. In addition to the aforementioned two major types of initiators, management level employees appear to be another special type of initiator. Higher ranking management occasionally initiates as well as approves wire transfer. And then the next attribute is the indicator of auto approver. These attributes indicate whether the approver is an automatic system or a person. It is defined by using the characteristic of the approver identification. Very similar as the automatic indicator, for a regular person, the identification would be numbers, and an identification of an automatic system can be alphanumeric. In addition to the aforementioned two major type of approval, management level employees also appears to be another special type of approval. And then the last attribute selected is the number of approvers. This attribute provide information on the number of approvers for each wire transfer. Depending on the nature and the type of wire transfer, different number of approvers is needed. It is reasonable to assume that the higher the risk of wire transfer transaction is, the larger number of approver is required. Then let's take a look at the anomaly detection procedure of this case. Usually, how to define an outlier or anomaly is considered a controversial issue in research. Different research questions and domain knowledge can lead to different definitions of what an outlier or anomalous observation is. When dealing with data with continuous values and a normal distribution, an outlier could be values which are two standard deviations above and below the mean value. When data are categorical, however, defining values above or below the mean would be impossible. In this wire transfer dataset, most data are categorical. The clustering procedure was done during the combination of categorical and numeric attributes. In order to identify anomalous activities in the wire transfer dataset, four identification methods are used. The first method of detection is based on the assumption that normal data instances belong to a cluster in the data, while anomalies do not belong to any cluster. Then we use algorithm called DB-scan, which stands for the density-based spatial clustering of applications with noise. It is a type of density-based clustering and doesn't require an input of the number of clusters in the analysis. Moreover, it can find arbitrarily shaped clusters. Because it also has a notion of noise, it can also be used for anomaly detection. Then the second anomaly identification method is the distance-based outliers. In this method, we define the outliers as individual wires which are far or different from other wires in the same cluster. And the third method is cluster-based outliers. The clusters which are populated by less than 2% of the total wire transfers are identified as possible outliers. The percentage is set arbitrarily based upon evaluating the results. For consistency of the evaluation throughout the study, cluster which comprises of less than 2% of the total population are considered as possible outliers. Then the fourth method is the statistical-based outliers. The statistical-based outliers are the wires which amount is more than 2 standard or less than 2 standard deviation away from the mean of the transfer amount of each cluster. For the last three identification method, we use a clustering algorithm. It is also the expectation and maximization algorithm. And for the first identification method, we use the DB-scan as a clustering algorithm. Then we'll compare and evaluate the anomaly detection result of all these four methods. Okay, here shows the results. The first type of anomaly detection technique is based on the assumption that normal observations will be grouped into clusters while abnormals would be discarded. So the first set of the results finds 49 clusters based on DB-scan technique. The largest cluster consists of 60.86% of the population. The remaining clusters each comprise between 0 to 10% of the population. 5 clusters contain more than 1% but less than 5% of the population, while 2 clusters contain more than 5% but less than 10% of the population. What DB-scan considers single observations or points as noise. The algorithm evaluates each individual point as core point, border point, and noise. The cluster results show that there were 341 wire transfers discarded as noise. Like here, this. Then let's take a look at the second result. This result, according to the distance-based outliers, that the possible anomalies are identified as single wire transfers that have low probabilities of belonging to its assigned clusters. If the probability of the wire belonging in the assigned cluster is less than 0.6, it will be flagged as a possible outlier. And these are the number of outliers detected using this definition. Then for the cluster-based outlier, the possible anomalies that are identified as clusters are those smaller in size, such as having less than 2% of the population as the member of clusters. The clusters which fall into this category are cluster 1, cluster 4, cluster 7, cluster 11, cluster 12, and cluster 13 with cluster numbers as 24, which is 0.25%, and 39, which has 0.41%, and 97, which is 1.303%, and the cluster 11 is only have 5 numbers, 5 points, which only occupy 0.05%, and the cluster 12 have 106 points, which occupy 1.12%, and the cluster 13 have 32 points, which equals to 0.35%, 34%. While in the fourth method, the means and standard deviation of the wire transfer amount of each cluster are calculated. The wire transfer, which have the amount above and below 2 standard deviations of the cluster mean, are identified as possible anomalies. The results are shown here. It's understandable that in the case the larger cluster will naturally yield many possible anomalies. On the other hand, even though some clusters are very small, There can also be possible anomalies present. For example, the class 1, class 4, class 7, class 12, and 13. This table presents the results of different specifications of the anomalies on a single clustering result. The expectation maximization clustering is applied first, and the clustering result is then examined. 3 different assumptions of anomalies are used to identify some observations as possible anomalies and outliers. And the results are shown by cluster. You can see that when we're using different definition of outliers, the outliers detected are different. And the number of flagged wire will be selected for further investigation to check if they are real anomalies. So all these transactions need to be checked to see whether they are real anomalies. So in conclusion, clustering as an unsupervised learning algorithm is a good candidate for fraud and anomaly detection. But without further investigation, there's no way to know for sure that a particular transaction is fraudulent. In other words, the transactions are not clearly identified as fraudulent or legitimate. It is often difficult to identify suspicious transactions. Clustering could be used to group transactions so that different attentions and strategies could be applied to each different cluster. Outliers or anomalies could be identified. Well, according to these 2 applications, we can see that clustering is a useful technique for the accounting profession. It could be used in the area of automatic detection and continuous control and monitoring area.